10 seconds of black. You won't have to worry about any of this. I'll come in, pre-roll all of this. But if for some reason they need to get going and I'm not here, you don't even have to run the titles. You can just come in here and press this twice, and that once, and then, and normally I won't pause these. Like if they were ready to go, can you do me a favor and go see if you can turn that light on over there? Yeah, I do. It's right over here.
Okay. Ralph Velli, New York, and as a hobby, I kind of make protocols. Anyway, to get started. This protocol is it's a text-based protocol, testing. Basically, the protocol is designed to be a binary protocol, but I started out designing it as text because it seemed simpler at the time, being that I wouldn't have to develop a client and a server at the same time. I could just telnet to the thing and see if it worked. Anyway, the protocol is called Textella. As it sounds, it has some Nutella roots, hence the Telia. Text meaning it's a text protocol. Okay, so we'll get started here. It's kind of a mix between IRC and Nutella. It's not for searching for files. The ultimate goal is to join channels just like IRC. You got ops and you can ban people and kick people and blah, 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 blah. But we're trying to do it in a scalable manner. Okay, so we'll start the talk here. We'll start off with an overview. I'll probably ask if anybody has any questions. The talk is divided into maybe 4 or 5 parts, so I don't want all of you to save all your questions to the end. And obviously, if there's not enough time, you guys can come find me wherever, and ask away. Okay. Textella is a channel-based partial mesh TCP network that addresses the scalability problems of IRC networks. The basic idea is to reduce the server to user ratio. At the time of this writing, which was actually a while ago, the FNet IRC network had about 120,000 users on it on 61 servers, yielding about a 2,000 to 1 user to server ratio. Because the IRC server structure is a tree, Basically, that's the minimal amount of server-to-server links that you need to keep these guys connected. This means blah, 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 blah. Okay. However, the Textella network is not forced into a tree, as you can see. There's no difference between the red and the black lines, if anybody was asking about that. Basically, the black lines were the fastest path that that particular broadcast spread to all those servers. The red lines are just equally as you know, they're just TCP connections between the servers. Textella can have anywhere between the minimal amount of connections, which is the same as IRC, which is basically n-1, and the maximum amount of links would be a full mesh, which is also not very scalable, but that is, you know, n times n-1 divided by 2. So basically somewhere in the middle is the scalable structure that you want, the partial mesh, you know? Channels themselves maintain tree structures, however, because you want to make sure that the traffic is always in sequence. You never want to make sure anything gets out of order, and pretty much I'm not about to start sticking sequence numbers on everything and reinventing TCP. Let's go on here. IRC constructs channels based around the idea that the network is already loop-free. This means that a simple join broadcast is enough to construct a loop-free channel design. IRC networks have global channel presence, meaning if you join a channel on one server, all servers are aware of this. However, on a Textella mesh, it is not simply enough to broadcast that you have joined the channel. Textella introduces the concept of looking for channels, finding channels via various paths, and locking down those paths to form the actual channels. To start a new channel, which doesn't exist, obviously you're not going to find it. So you need a join command, pretty much. It's like a local join. It would be like joining a local channel on an IRC network. Only the server that you're connected to is aware of it. If somebody else on the mesh on another server tried to join the same channel name without actually looking for the channel, they would create two separate channels with the same name on two different servers. Okay. To find a remote channel, you must query for the channel. This query broadcast will respond with 0 or more query hits. Each query hit represents an individual path to the channel that you're looking for. A circuit link is then used in reference to the query hit to create the inter-server channel. Channels are time-stamped and everything, so you don't have to worry about losing ops or anything like that. The oldest guy wins, just like typical time-stamping algorithms. All right, before I show any demos or anything, I get some of the other simple stuff out of the way. The basic overview of the network server daemon. The server was written in C. It's under the GNU public license. There's a simple select loop for I/O multiplexing. Obviously, I use all non-block sockets and everything. I'm not a huge fan of threading and all that crazy mutex stuff you got to deal with it. Configuration file is a simple text file and it reads just like everything else. Basic overview of the network protocol. The protocol uses simple text, it's named Textella, with carriage return terminations. Network uses traditional IP version 4 TCP links. I didn't even get around to IPv6 yet. All right, the network fabric can have anywhere between a tree's number of links and a full mesh link count, which I already stated pretty much. And although the talk says it is a peer-to-peer structured network, we still have servers and clients. The network is a server, client, blah, blah, blah. The decision was made against a true peer-to-peer system in order to avoid clients transiting channel traffic after they leave. Because clients have a nasty little business of leaving whenever they're done doing their thing. Okay, I'll start off with the basic Nutella network theory because pretty much channels are built on top of that. ping and query commands are initiated by clients. They are broadcast out to all neighboring servers with a unique 32-bit random ID number and a time-to-live variable decremented on each hop. The ID is used. The ID is associated with each broadcast. It's basically used as a poisoning mechanism to make sure that the broadcast is driven outward and never looped around in circles and over and over and over and over and over. A broadcast will never propagate from the direction that it came from, something similar to like split horizon, you know. If a server receives a broadcast with an ID number it has already seen, the broadcast is dropped because it went around in a loop, so there's no need to say it again. Forward propagation is terminated if a time to live of 0 is ever encountered, basically. That's to prevent broadcasts from spreading wild, you know? Did I lose my place here? Okay, the pong and the query hits. Basically, ping and pong works like the Nutella ping pong. You use ping pongs to find other servers on the network. You send out a ping broadcast, and you get a series of pongs back saying, hi, I'm server this, hi, I'm server that, whatever. It's very exactly similar. It's exact to the Nutella. It's not a very important command. It's not really used for anything. It doesn't use... the creation of channels have absolutely nothing to do with pings and pongs or any of the networking viewing functions or anything along those lines. Pongs and query hits are both unicast commands, meaning they spread along a straight path. They're not broadcast to multiple servers or anything like that. They're in response to a broadcast. They use the ID numbers of the pings and the queries to propagate back to the originators of those broadcasts. In addition to this, query hits create additional paths back to the originator of the query hit through use of a second ID. It's similar to a Nutella push. And on to the push. Push is a simple unicast command that is initiated by a client in response to a query hit. Push commands use the IDs associated with the query hits to propagate back to their original point. The Textella counterpart to the push command is the channel synchronization negotiation initiator called circuit link. Okay. We'll start with, well, you know what, let me show you what a ping and a pong and all this stuff looks like, because picture's worth 1,000 words. Okay, so have here 21 servers in a random mesh, as you saw earlier, on this little laptop I got here. We'll connect to one of the servers. What I just did was a basic little handshake. Red is the flavor, I call it, of the protocol. Basically, going by the Roy G. Biv standard. Red being the most primitive version of this protocol. It's basically in its infancy. You declare your nickname, blah 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 blah. You see the server connection, and there's a ping. Now, let's see, what do we have here? Output 1134, pipe, Perl, RM, enter, pipe, less. Okay, there's all the negotiations, servers connecting to each other, blah, 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 blah. Okay. All right, that's me looking at the graph. Where is it? Okay, here we go. All right, as you can see here, there's the ping that came from my little telnet client that connected to the server. First thing the server did was it turned around and it sent pings to all its neighboring servers. It there's the unique 32-bit ID to make sure that the broadcasts are never looping around and causing problems. And we send a ping ACK back to the client. That's this little guy right here, just so you can tell the client which ID it's going to expect. It's not a really it's not an important thing or anything, but a couple of my client developers asked for it, so I gave it to them. Anyway, you can see here's the Pongs coming back from neighboring servers, and they end up getting delivered to the client. In from a server, out to the client. Okay, that's a ping and a pong. Pretty stupid. Okay. Now we're going to start talking about channel mechanics, and I'll show you how channels actually connect and synchronize and work, and all that fun stuff. Channels are pretty much easily able to divide them into 3 layers. Layer 1 consists of the commands used to bind the sockets to the channels and tear them down when it's necessary. This layer is also responsible for timestamping and mode negotiation. The commands that are part of this layer are circuit link, circuit live, circuit override, circuit kill, merge in, and merge out. I'll show you what all those commands do in a little while. The second layer consists of commands used to ensure that the channel maintains a loop-free tree structure. These commands also make sure servers have a unique ID on a channel, basically nickname collisions. You can't have 2 people with the same nickname on the same channel, because then you can't private message them. Those commands include servlink, servlink, which basically introduces a server to the channel, removes a server from the channel. Userlink and userlink, which introduces users to the channel and removes users from the channel. The third layer consists of commands that are used on the channel itself. Message, private message, whois, trace, mode, kill, kick, topic, all those sorts of commands. Okay, now we're getting into the channel mechanics, how the channels are actually constructed. Okay, we'll talk about the synchronization negotiation sequences. In order for a channel to transit traffic properly and to avoid feedback loops, topology maps must be exchanged between all servers participating in the channel structure. During inter-server channel creation, the circuit link, servlink, userlink, topic, and circuit live commands are propagated in that order in a forward direction. Upon receiving the final circuit live, a circuit override is optionally propagated backward if modes or timestamps need to be overwritten. Serverlink, userlink, topics, and server lives are then propagated backwards. After back propagation has completed, the forward propagation begins again. This method of sequencing out the forward then back synchronization process is necessary essentially to give servers a chance to see if you should be allowed on the channel or not. A ban or mode restriction from an older side of the channel could keep you off it. Sequencing ensures that you don't get a short glimpse of the channel's members before a ban or mode is synced. At the channel point of contact, normal back propagation is performed. The merge in, servlink, userlink, topic, and merge out commands are then injected into the channel. These commands are propagated throughout the channel in a similar sequenced manner. However, there is no need for back propagation because we're not creating, we're just informing. That was kind of a mouthful, so let's just show you what I was actually talking about here. Okay. Here's my Remorse client. Going to join a channel. I'm the first one on that channel. Thus, I have ops. Here is the introduction that I say of myself onto that channel. The default channel modes that come down to the client, and a empty topic with a timestamp on it and who it was set by, which was the server itself. Not very interesting yet. So, create another client, host, on a foreign server. It'd be nice if I could spell local. Okay. Oh, man, come on. Okay, I have a second client called RMRS who just connected to another foreign server, wherever that was. First thing we're going to do is we're going to look for the channel. We send out the query broadcast. What we're seeing here is a whole bunch of paths over that mesh to the other channel. Let's see if I can find it on the graph. This guy down here, all right, that's 1134. That is where Remorse is. And let's see where 1154 is. Oh, you know what? I'll just let that regraph. Oh, wait. Okay, what I just did was I joined the channel across the mesh. You can see I picked a path that I found. I used the ID that was associated with this query hit to pick the path. I see myself join the channel. Initially, my server was not aware of any of the timestamps, what the channel looked like, or anything like that, so it gave me ops. It set the modes, and it gave me a blank topic. The next thing I see is I got de-opt all of a sudden, because the other client was older than this client, and the timestamps prevailed. And I see the other client join with ops. Let's see if this graphed out yet. Yes, it did. Okay. So as you can see here, we'll zoom in. Here's my little Remorse client. This little blue dotted line is the channel. Go back to the original view. You can follow it all the way over here, and it does a little squiggly thing over here. Hits this server, which is on port 1154, and there's my little RMRS client. Let's take a look at the synchronization sequence. I guess we'll try it from, let's try taking a look at 1134 again. Okay. Now, if you recall, I initiated this inter-server channel from 1154. So from 1134's perspective, this is what it sees. Send 1134, blah, blah, blah. Okay, there's Remorse. This is basically just showing you the tree structure. You got 1134 introduces itself. 1135 is connected to 1134. 1137 is connected to 1135. 1154 is connected to 1137. And there's Remorse. Let's try it from 1154. Pipe. Ooh, it'd be nice if I could spell here again. Okay, where are you? You're up here. Okay, here's the juicy stuff.
client from 1154 says, circuit link to this ID, pound havoc. First thing the server does is it turns around and it sends to one of its neighboring servers, circuit link, the ID, the path that you're following back, timestamp of the channel, name of the channel, 7 hops, the modes of the channel. It introduces itself as 1134, and it says, I have a user named RMRS, hanging off 1134. Here's his timestamp. Here's his user modes, username, host name, channel modes, real IP. There's your topic, and it caps it off with a circuit live. Then it turns around and it says immediately to the client that's connected to it that it's joined the channel. There's pretty much the default modes, no topic. Next thing you see is a answer coming back from the neighboring server saying that there's a circuit override because it has the same timestamp, and channels with the same timestamps merge their modes, which is why you see an override. No topic, circuit live out. At this point, it's considered a connected channel, even though there's nobody else on it yet. So we start getting merge-ins from the neighbor because the channel is still being built out towards the other client. You see, 1135 is introduced from server 1137. No topic again, merge out. Another merge in, because it happened pretty quick, 1134 is connected to 1135. 1134 has the user Remorse on it. There's his timestamp. He's got ops. And as soon as the server saw that, it knew that it had to remove the ops from RMRS because of the timestamps. Then it showed that Remorse joined with a +O. Okay. So now you have a basic idea of what the synchronization looks like. And I can continue. Blah, 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 blah. Okay. Propagation suppression of pre-synchronized channel nodes. Natural channel traffic must not be propagated to nodes that have not yet finished their synchronization sequence. This is because it is not until the end of the sequence that you can guarantee that the channel is loop-free tree structure. Channel pruning algorithms. Channels in this flavor of Textella, as I alluded to before, the red flavor, are considered to be multicast channels in the sense that they do not exist globally across the network fabric. However, they're allowed to. If you've got people on every server and they're all on the same channel, there's nothing that prevents it, but there's nothing that forces it, which is important. Pruning code is executed when a node is removed from the channel's node chain. This code ensures that there is never a stale branch off to a server where it's no longer needed. Basically, the idea is every time you see a socket from a channel leave, you run a test on the channel, and you say, is this channel only one server? And if it is, kill it, because you're a branch off to nowhere. If you were doing anything useful, you would have had users or other servers connected to you, being that you were either providing traffic to a user or acting as a transit server, passing traffic through you. So we'll start with some more synchronization here. I'll show you a third one. Okay. Let's pick a channel here. Let's try 39.
as you can see, we got a whole bunch more query hits this time. It's because there's a lot more paths to the channel, because it's not a dot on the network anymore. It's a line on the network. It's a bunch of servers. So there's a whole bunch of paths. So we'll pick one at random here. We'll try this one. Looks good. Open up a circuit link to it. Pretty much what the user sees. It's self-joined with ops, topic, blah, blah, blah. It lost its ops. Remorse came in with ops, and RMRS came in with no ops. So as you can see, the channel is still synchronized with only Remorse having ops. Take a look at that from all the other ones too. Pound Hammock. Oh. Also got who working, so you can do that. They're identical to the IRC commands pretty much. And let's take a look at the synchronization sequence that's going on there. Let's take a look at the links of the channel here. It's important to keep in mind that IRC networks, the entire network has a links, a tree structured links like this. Every channel on Textella has its own links. So every channel could be going in different directions, moving however it wants to over the mesh. It doesn't make any they're independent of each other. You can almost think of them as little virtual IRC networks on top of this mesh. Anyway, let's see what we got here. We got 1134 with Remorse on it. 1135 is connected to 1134. 1137 is connected to 1135. 1154 is connected to 1137. You got Remorse hanging off that. 1152 is hanging off 1137, 36 to 35, blah, 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 blah. Let's take a look at one of these servers. We'll take a look at 1136 because it's transiting traffic. Where is my debug here? 36. No. Okay. All right, let's try to go through this synchronization sequence because it looks kind of long and interesting, and it'll give me something to talk about, right? First thing this server sees is a circuit link coming in that's referring to a query hit that passed through it earlier. Server 1140 introduces itself. Then it says that it has 1139 connected to it. Then it says it has Remorse 04 hanging off 1139, timestamp, blah, blah, blah. Topic, okay. Circuit live in to cap off the sequence. A circuit override is sent back. The server is announcing itself, 1136. Circuit live out caps off that sequence. The next thing it does is it turns around and it begins forward propagation again. The circuit link, you can see with the same descriptor ID, pound havoc, there's your timestamp. It announces that it itself is named 1136. It has 1140 connected to 1136, 1139 connected to 1140, and Remorse hanging off that, and the topic. Come down a little bit. The next thing we receive is a circuit override from our neighboring server that we just propagated to. Where was it? Did I just lose my place? Here we go, right? It's announcing that its name is 1152, and that's it. Not too much interesting. The circuit is then said to be set up there. So we start seeing merge-ins coming in because the channel is still being built outward, but there's no need to actually do any binding or circuit things or anything like that related to the local server. So we see a merge in come. 1152 is hanging off 1136. See the topics. Okay. We see another merge in. 1137 hooked off 1132. Blah, 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 blah. Now, let's take a look at this graph again and see what the channel looks like now.
And that takes a little while. Okay, that one's done. Well, while we're going, I'll start talking about some interesting bugs discovered in development. Inherent broadcast propagation problems occur under certain memory constrictions. The Nutella broadcast theory has within it a fundamental flaw. Servers cannot remember an infinite amount of broadcast identifiers. They must eventually be queued out or timed out. A broadcast, this is going to sound a little weird. If a broadcast can survive in the network fabric long enough to loop back to its originator after the broadcast identifier has been forgotten, the poisoning mechanism that drives the broadcast outward is then defeated. Once this occurs, the only thing that prevents infinite regeneration of that broadcast is the time-to-live mechanism. The segment of the network is crippled under its own DOS attack for the life of the broadcast. This sounds like a bug that you would never run into. I ran into this bug. Basically, I was testing sendQ code. I wrote internal buffering for sending whatever to clients or neighbors, and I wanted to test it out. So I figured the best way to test it would just be to send as many broadcasts as I can, because broadcasts generate a lot of traffic back to you. Anyway, I dropped megs and megs and megs of broadcasts, and the send queue slowly filled up, as it should, because my client could not keep up with it. And when you hit whatever the ceiling of the send queue is, it's configurable, it's in the configuration file. You got to kill the client. So the client dies, and I still had a whole lot of traffic coming back destined for that client, because the only server on the network that was aware that that client was dead was the local server that it was connected to. So I thought it would be a good idea to make a command that propagated outward when the client died, that basically said, kill the path back to the client. And that's when I ran into the bug. Pretty much what happened was you get a whole series of broadcasts that were spreading outward. The client send queue filled up. The server killed all the broadcasts that were associated with that client and started sending out a broadcast that was chasing the previous broadcasts that were spreading through the mesh. The first broadcast that the client sent out came back to the original server, and because the server already killed it, it thought it was a new broadcast. So it grabbed it, it remembered it, and it propagated it to its servers, all its neighboring servers. And since that the command that was used to tear down that path, that broadcast path, was also broadcasted to all the neighbors did the same thing. So the network basically DOSed itself to death. It eventually stopped after about a half an hour, and this is with a time to live of 8, all right? Not a huge time to live, but without that poisoning mechanism that keeps broadcasts from spreading around, and you have a network that looks like this, it's a lot of regeneration. Anyway, what I ended up having to do was basically say, keep the broadcast identifier in memory, but forget where it was coming from. Anyway, take a look at this channel here. We got Remorse connected to 1154. That goes over to this server. Can I see that? Okay. This server right here, if you zoom in, you can see it's kind of a transit server. It's got multiple connections to it, but it still maintains a tree structure. 1137 follows over to this guy over here. 1135, which is connected to 1134, which is connected to Remorse. Oops, wrong way. And then you can see a whole mess of connections in here. This one goes there, that one goes there, that one goes there, over to the other client over here. And the leg bone is connected to the hip bone, blah, 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 blah. Anyway, let's talk about the consequences of the absence of global network visibility. Scalability comes at a price. The price is the absence of global network visibility, basically. Collision domains for nicknames and server names have been localized to the channel, not the network. This means that a remorse on pound havoc can be a totally different remorse than one that's on pound Textella. A server a user is connected to is the only server that is aware of all the channels that the user is on. That means if you want to whois somebody and have that work properly, all whoises have to be remote whoises, because only the server that you're connected to is aware of all the channels that you're on. Well, let's see what else we got. Well, that's more or less it. I mean, does anybody have any questions, first of all? Is there comments or anything? No? Yes, Ian.
For this, besides IRC, like perhaps...
That is a very, very good question.
Can you repeat the question?
Excuse me?
Repeat his question, please.
Repeat his question? He wants to know, what's the point?
Is just for chat. And no, it's not just for chat. This is basically a testing protocol. I wanted to make sure that the signaling system worked. What I'm basically trying to do is make a binary scalable version of IRC so you can drop things like MPEGs and MP3s on the channel and have the channel do the relaying for you. You could say, what's the point of that? Basically, the idea is something like, let's say you want to run a shoutcast server or something like that. You could drop it on a channel, and you don't need the bandwidth for everybody to listen to you. The network does all the splitting of the signals, and you don't really care. You just say whatever you got to say to the channel, and that's pretty much it. The channel does the rest of it. The channel does the regenerating of all the signals and all that good stuff. Obviously, this is kind of ridiculous. If you start thinking about like MPEGs and stuff like that, take like an MPEG that's, you know, I don't know, like 500K a second or something like that, and you're on a channel with 30 people, that's a multiple. That's 30 times whatever if they're all spewing out MPEGs at the same time. That's a lot of traffic. So obviously throttling and all that stuff has to be built into the network and all that stuff. But this network is in its infancy. I know I've been working on it a while, but I wanted to make sure that I could make a scalable version of it first on a text-based thing, so I wouldn't have to develop clients and servers at the same time, protocol dissectors, all that fun stuff. You know, it's much easier to just write the stupid server and telnet to the thing to see if it's working than, you know, to write a client and a server at the same time and all that stuff. I wasn't about to start pouring all this code into something that, you know, for all I knew when I started making this thing, it might not work. You know, it was just theory. It was just on paper. It was on paper for a while. But it seems to be working, and that's about it. So any questions or comments, or does anybody have anything to say? No? Yes?
So what are your plans for development? How are you going to proceed with development? Do you have people on about applications?
That's a good point. Well, basically, the whole idea is the Textella project is a precursor to the Streamtella project, which is the binary version of this. Pretty much what I'm going to do is I'm going to take kind of like a port number and associate it with the channel name. And that's going to tell you what type of traffic is on that channel. And the servers really don't care what the traffic is. So whatever the clients want to do with it, that's, you know, the client's business, I guess. I plan on hopefully, writing and supporting at least a couple of clients, but I want this to be as open of a protocol as possible, I mean, if TCP was proprietary, we would be pretty lost, So anyway, that's pretty much it. So this is pretty much just my hobby, it's not my job, obviously, but so it's moving a little slower than I'd like to, but a lot of this stuff is coding, testing, recoding, testing, recoding, and round and round we go. And that's pretty much it. There's only about 3 minutes left of the talk, so you guys can, yeah, Ian, what's up?
Webpage, or how do you communicate with your developers? I mean, do you have a Subversion site?
Yeah, if you wanted to grab the source code to this, you can. I gave it to the to Hikari, so I think that'll be included with CDs and all that stuff. But if it's not, you can grab it off of textella.com/download and take a look at the source if you want. Yeah.
One more question that
Yeah, no, please.
might be good for this crowd. What's your intentions as far as security and privacy on the network? And when implementing that, can you speak a little bit what your plans and your viewpoint is on that?
As far as security is concerned, I guess that's an allusion to encryption or something along those lines. Encryption would definitely best be handled at the endpoints. There's nothing that stops you from S-tunneling, server-to-server connections and all that good stuff. And I definitely plan on building that kind of stuff in there. But as far as where I stand right now, I'm still in the early development stages of making sure all the commands work. I don't even have a complete total, and I don't have a complete and total protocol command suite right now. So, sorry.
Server authorization on the network?
Yeah, no, I was looking into that stuff too. It's very, very similar to IRC, the way IRC is set up. You have your I lines, which basically say like, okay, I'm allowing asterisk.com. Throw them into, whatever this class is, and the classes define, kind of like what their certain properties of it, how often the client gets pinged, that type of thing, the keep alives rather. Send queue, how big the send queue should be for the clients, who you can allow on, who you can't. You can ban people off the networks and all that stuff. There's still certain theoretical dilemmas I'm working on, like how to deal with rogue servers and all stuff like that, nasty admins and all that good stuff. But it's like I said, the protocol is still in its infancy, and I know I got a whole lot of work to do on it, but for some reason I actually kind of find this stuff relaxing. So it's kind of therapeutic for me to just sit around and code and stuff like that and play around with this stuff. And that's pretty much it. Well, it looks like it's 5:50, and you guys got 10 minutes to get to your next talk. Thank you. Thank you.